And this is a shot, of course, of energy. This is a lightning bolt that I somehow by chance managed to catch on the camera. Thank you. So we have talked about energy before, and we've talked about the waterfall analogy, where at the top of the waterfall you have water that's potential energy, and then the water is no longer bound by the underlying rocks. It goes over the fall, and the potential energy is converted to kinetic energy, and that kinetic energy can be tapped. And in fact, in the case of Niagara Falls, they've got a tunnel way upstream, and a lot of the water that goes that would have gone over the falls instead goes through this tunnel and goes to a hydroelectric plant. And in fact, the water that actually flows over the falls only flows over the falls because people that run the hydroelectric plant allow it to. They actually could be tapping every single amount of water that goes over the falls and using it to make electricity. But they don't for basically aesthetic reasons. And they allow more water to flow, I believe, during the daytime than they allow it to flow at night, because it's during the daytime that people are out looking at the falls. So there's a number of ways we can use that analogy and use it to look at biological systems and what's going on there. Crucial to understanding how organisms work is realizing that there is potential energy, and that potential energy can be tapped. It not only can be used to do things, but it can be converted into other forms, and these other forms may be more useful as energy sources to an organism than their original forms. So one way that organisms take supplies of energy and work with them is to convert those supplies from a chemical form into something that it still can be a chemical form, or alternatively can simply be a form of energy that's being directly tapped. And one thing you see a lot of is molecules that contain lots of energy. In molecules that contain lots of energy, organic molecules, what you're going to see is a lot of these carbon to hydrogen bonds. When we looked at lipids, we saw a lot of carbon to hydrogen bonds. I said that's an indication that these molecules have lots of energy associated with them. When we looked at carbohydrates, there were some, not as many, but also some carbon to hydrogen bonds. And so these are the bonds you're looking for. These contain what can be described as reduced bonds. They're actually bonds that contain a lot of energy. And I'll get to what reduction means in a bit. So we have essentially energy that's been locked into chemical bonds. When you're eating something that's high in sugar or high in fats, you're eating a lot of molecules that have a lot of energy locked into chemical bonds. The trick is to get the energy out of those bonds. And what you do essentially is the same kind of thing as you have with the waterfall. You have this potential energy, and then you allow or do something that allows the energy to come out of those bonds and be tapped in some other way. And the way we do this is a process known as oxidation. So reduction is the opposite of oxidation. Reduction is actually the gain of an electron, and oxidation is the loss of an electron. And we take these energy-rich organic compounds and we oxidize them. Specifically, we oxidize them to water and carbon dioxide. And so in the process of taking the energy out of these organic compounds, one of the things our cells do is they take the electrons, and once those electrons have used up the amount of energy, or they have had the amount of energy they started with tapped out of them, we then have to get rid of those electrons, and what we do is we donate those electrons to oxygen. So in a sense, we have a lot of movement of high energy electrons that are locked into bonds. The energy then is tapped out of those electrons. The electrons, in a sense, are going over the falls. They're becoming less energetic. And when they're as inenergetic as they're going to be, we get rid of them by feeding them into oxygen, the oxygen we breathe in, molecular oxygen, to create water. Now, how do you get the high energy organic compounds to begin with? Well, the answer is you have to take the low energy electrons and pump energy into those electrons and then lock those higher energy electrons into chemical bonds. And this is done by a variety of means, but the most consistently or greatest use is of sunlight to do this. And that's a process known as photosynthesis. In photosynthesis, you take light and you use the energy of light to take electrons and move them from a lower energy state to a higher energy state, and then you lock that energy into chemical bonds. And then we, the consumers of plants, then take those high energy electrons that are locked into these bonds and allow the electrons to come out of these bonds and eventually donate the electrons to oxygen. And in the course of moving from being in these high energy bonds to these low energy bonds, from being in a reduced state to an oxidized state, we pull the energy out of those electrons. So continuing with this analogy, so one of the things that we do when we are pulling energy out of the electrons found in these organic molecules is we use that energy found in those electrons to pump protons. So you just saw this. So we pump protons across membranes, and in fact we use electron transport chains or electron transport systems to pump these electrons. So this is an electron transport system. So we basically take protons that in this case are on one side of a membrane, and we use energy that's in electrons that we've taken out of these molecules that have high energy electrons in them. And we use that energy to pump protons, and we trap those protons on one side of a membrane. And then we allow the protons to flow through the membrane as though they are flowing over a fault. And instead of having a hydroelectric power plant intervening, we have those ATP synthases, which we just saw. So we take chemical bonds, lots of energy, we take those electrons and we pull them in a sense towards oxygen, and in the process of moving from being in the CDH bonds to being in bonds with oxygen, we tap their energy off. We use that energy to pump protons. The protons, in a sense, are charging up a battery, and then we allow that battery to lose its energy in the process. What it does is it powers the turning of the ATP synthase, which takes a molecule called ADP and converts it into a molecule called ATP. Complicated, I know. But this is the way it's done.